So we have a ball bearing. I hope you all have seen the ball bearing.
Yes, sir.
Yes.
And what is interesting about ball bearing is that the two circle, which you see the inner circle and the outer circle, they can move independent of each other because the ball will facilitate this motion. Both can roll in any direction they want. The motion of the outer ring will not be affected by the motion of the inner. So generally, in reality, what happens like the inner ring is mounted on a axle of maybe bicycle hub. It is mounted kind of thing. It is also mounted on some sort of rickshaw. These are the steel balls which are seen as bright color circles. And now this is the ground, and this is the radius is r, and maybe 3. And 2R. So now imagine this is given that it's moving on a surface with angular speed omega, and this is the case of pure rolling. And it is also given that the inner ring is moving with angular velocity omega. Right? These are two omegas given, and everything else is given to you. And now I may ask you this question. Let's say this is 30 degree, and you're supposed to take this as XY plane. So what is the velocity of point? Solve this question. Done. Anyone getting the answer? Okay, so what is the constraint relation here? What is the condition for pure only? Tell me, guys. What is the condition for pure only? The velocity of center must be equal to how much? What you need to realize that VC must be equal to
omega into 2.
2 omega. Yeah, omega into 2R. So the bottom is 2R away. So bottom is trying to go backward with velocity 2 omega. So the center must move by the same value, then only it is possible. So this is something like unset truth. So we can go to the next part. So for point P, the motion with the respect to center is something like this. But the center itself is going this way. Understand? So the point P will have two velocity, one towards right, another omega r this way. And therefore you can easily resolve into components. So Vp we can write as Vc I cap and then omega r sin 30 minus I cap.
So
And
omega by
omega,
2r
pardon?
in position of p, the velocity is omega by 2r, na?
Yeah, omega by 2, correct. Omega r by 2, correct. So now just need to substitute the value. So omega r by 4, how much is this? This is the JE advanced term of 2012. It is clear?
Yes.
Okay.
Sir, I want to know the last thing. Noted, sir.
All right. So, so now we have something like a bobbin. This is the inner cylinder and the outer is just a like disc. So it's the same question, but this time it is not a free ring which can rotate. It's like a fixed rigid body. So now if I say this is omega, and if say inner radius is r and outer radius is 3r, and this is omega. And now let's say you choose a point somewhere here. And this makes an angle 60 degree. So find the velocity point P. So, yeah, do this question. Okay, actually you can take the velocity point P on the inner point. I bet. No, but anyway, you can do this question now. So if you can do this question, you can do all of the questions. Just wait. Let me make it. Yeah, take the point P here, and this is let's say 2r. No, it's not, because 3r is the outer periphery, and r is the inner. Then 2r is somewhere in between. Not do this. Tell me the answer.
So is it 3 omega r plus the root 3 omega r I cap minus of omega r j cap
3 omega r I cap is the right part.
plus
Yes.
the root 3 omega r I cap minus of omega r j cap
Plus root 3
omega r
omega r
I cap
I cap.
Sir, I
minus
got
of omega r
Yes.
j cap
Yes. I cap and then
minus of omega r j cap.
oh, yes.
sir, I got 3 omega r minus root 3 omega r I cap plus omega r j cap.
No, it's I think sign convention I've taken now, because I have taken the clockwise motion. So P point will move this way,
Oh, oh,
and you have taken otherwise.
yes.
So of course this will be 2 omega r, because omega is the angle visible, and the distance from this is 2r. So this is 2r. Now, yeah. So now you can resolve. So this is 60 degrees. This is I think this is also not correct because this will become 3 omega r I because of the center. So this will be 3 omega concentration. And the 2 omega r cos 30 will come. No? The 2
Yes,
omega r cos 30, which is root 3. So root 3 omega r I cap. Yeah. And then omega 2 omega cos 60 or sin 30. It's the same thing. Yeah, that's correct. Okay. Okay. So what we can do next? The next concept is called okay, no. Okay. I just wanted to save the space. So now what we're going to do next is called the velocity analysis.
So,
Yes.
so when we draw a line perpendicular to the velocity of any 2 points, we get ICR, right? ICR, na, instantaneous center of rotation and instantaneous axis of rotation. But here we are
Yes.
not getting that point. Here the touching point is the ICR, na?
Yes. So you
But
can
when we
always
draw,
if you take any 2 point, let's say you take a point here, and if you take a point somewhere here, maybe top. So where is the ICR? Where is the ICR?
so it will be in the center.
So now these are the wrong dimensions. See, the problem is these arrows are wrong. You should realize that this is not the direction of motion. Okay, so that's the problem. So the topmost point will move like this. Let me show you. This point will move like this, but this point will how it will move? It will move something like this,
inward, yeah.
Yes,
and that is why if you do the normal, it will go through here.
yeah.
So
So we took first the pure rolling condition, and then
yeah.
we found two omega from the center, right?
So it is always the same definition. It will never change. Just because you have a wrong interpretation does not mean it's a wrong thing. Anyway, so now what we're going to do is velocity analysis for pure rolling motion. So let's say we have a ring which is going to perform the pure rolling motion. So what is the essence of pure rolling motion? What we exactly mean by pure rolling motion? On a fixed surface, the answer is pretty simple. When we have a fixed surface, so let's say this is the y coordinate, this is the x axis, x coordinate, no, x axis and y axis. A pure rolling refers to the condition when the bottom is not slipping. Now, if bottom is not slipping, so this will never go backward. So every point, if I just consider, this point will not go backward, but it will go only move forward. So in a way, you can imagine that this rolling motion is like a falling forward. So you can think like a fall forward. Now, what does it mean when we say fall forward? So if I look at this length of the ring, it will just fall over the surface. And because this is a curved part, So this point will fall below here or will it somewhere ahead? What do you think? Where it will fall?
Ahead,
Hmm?
somewhere ahead.
Exactly. It will fall somewhere ahead. So the idea is simple because it will fall somewhere ahead. So what you can think is this length, if you cut and if you stretch, it will fall, it will spread something like this. So if you cut this length, it will exactly spread by pi r by 2. It will spread something like this. If you cut till here, full value, it will spread till pi r. So if you cut full, it will spread up to
2 pi r.
So yeah.
exact. So that is the basic idea of pure rolling, that the body will unwrap itself over the surface. That's it. So in one complete rotation, how much path it will unwrap? So on what path it will travel? The answer is 2 pi r. So in the pure rolling condition, when the body moves, then the body exactly turns by when 2 pi in an angular state, the center mass goes forward by 2 pi r. So the body turns by 2, I mean 2 pi, and the translation of center mass is 2 pi r. So if the body turned by 1, it will travel forward by r, 1 radian. And if the body turned by theta, then it will travel forward by r. Okay, we didn't answer, right?
Yes, sir.
So let's see once again. Now this is something big realization, that in a pure rolling condition, things are just touching. So the surface, this part of this surface is touching the bottom surface, and therefore it will be slightly more because this is a curve and this is a flat surface. So let's say if we turn by just elementary values, maybe uh, if this ring is just, it slides forward, so you move the ring slightly ahead. I'm just moving slightly more so that I can represent some. So let's say the ring has moved from there to there. So the new bottom, the old bottom, this is, let's say the old bottom is here. This is the old bottom. You can see the old bottom. I hope old bottom. So now the old bottom, where you expect? So will it be at the bottom or somewhere behind?
Behind.
So I'm just representing the old bottom here,
It will be,
somewhere up, correct?
yes,
Yes.
sir.
Yes.
But the thing is, the bottom will never go backward. So now something which you need to realize, that from here you will never go backward. It will always go forward. So no point of the body can move backward. That's very interesting fact. Because V equals to omega, so the horizontal component of velocity is always bigger than the omega r component. So what does it mean is, if I just take a simple example, let's say choose some random point as of now. So let's say take this point. So this point will have two velocity, omega r and v. And why I'm writing v and v? Because you can understand that v equals to omega. So both are same, isn't it?
Yes, sir.
Yes, sir.
Now this point, if you think carefully, what is the net velocity of this point in the horizontal direction, right or left?
So,
Right.
So any point of the body cannot go backward. That's a very interesting fact. So although it is will have component backward, but the horizontal component on the right is always dominating because this is the some angle theta. So V is bigger than V cos theta, correct?
yes, sir.
And therefore it will never go back. It will only go forward. So in which case it can go backward? It will only go backward if the ring I'm drawing is like a bobbin. In bobbin, we have seen that the pure rolling will be happening here, and if the point is here, the omega part is not bigger. So omega is bigger here.
Yes, sir.
So this omega r is smaller, and therefore this component may exceed this value. For some angle, it will be bigger. So beyond some angle, it will become smaller. So it will go backward and forward both. So this point is very dangerous because this can go backward also and can go forward also. For some time it will go backward till the omega r cos theta is bigger than omega r, it will go backward. So now this will give the condition that cos theta is more than r by r. So till this value of theta, so when cos theta is more than r by r, so theta must be less than cos inverse r by r because cos is a decreasing function. So the inequality will change. I hope
So
you
can
all.
you explain this again?
So if we have a bobbin case, this is the bobbin question if you remember. And if I take the periphery and the center of mass is going forward with Vc, but this center mass Vc will be equal to omega r, where r is the small radius.
Yes.
But the point on the periphery, as you can see here, the point on the periphery, how it will move, this point, how to move. So it will move with omega r horizontal because of the center of mass, and in the frame of center, it will go like this.
Yes,
Yes.
sir.
Okay. So this is omega into capital R, correct?
Yes.
Now it is possible. Now this point will move backward when this component is bigger than this component, correct?
Yes, sir.
So backward motion. So this gives us a condition that cos theta is more than r by r. Now cos is a decreasing function, so when you take the inverse, the inequality will change. Nathan. Let's say
Understood.
cos theta is more than half, then theta must be less than 60 degrees.
Yes, sir.
And
Yes, sir.
this is the problem of trigo. If you know trigo, you can do this. It's a very basic thing in maths. Now, what I am saying now that if in my case of the ring example, for this particular case, every point will only move forward. There is no question of backward movement. This is my question. Are you getting my point? So this point will never go backward. It will only go
Forward.
forward. So you can think of a example. Let's say when you walk, your body goes forward. Okay,
Yes, sir.
your your rear foot or the back foot remains there only. Correct.
Yes, sir.
It never goes back. So when you lift, you're always forward. Understood?
Yes, sir.
Yes,
You're not walking backward. So you're no part of your body. In fact, your foot may not be moving, but no part of your body is going backward. So either it is not going backward or either it is rest or going forward. That's the scenario. Okay. So now we are supposed to analyze the motion. I want to just exactly know that what will be the exact path of this point on the periphery and how much distance this point will travel in one rotation. So these are the things which we are trying to evaluate or calculate. So okay, I'm not going to rub this part because this may be kind of help you in what we discussed. So let me do this again on a fresh page. So, pure rolling is something very interesting, and we should understand that okay, the motion analysis is the integral part of this chapter. In this chapter, there are so many facets of discussion. Like there are small, tiny concepts that need to be explored beyond your imagination. This is the radiuses are. You draw thin line just to, and probably how much you think. I mean, if you just do this should come somewhere here, something like this, and the down will be. This is yeah. So now this is the 2 pi r. I believe that this is the 2 pi r. So this will exactly unwrap up to here. So in one rotation, this ring will unwrap up to here, and this will be exactly 2 pi r, the length. But if I just choose a perimeter, like a point on the periphery, somewhere here, the bottom one, because this is what I'm trying to analyze. I just want to know how this point is going to trace the path, this point. So this point on the perimeter or periphery, how this will trace the path. So
Bouncing path.
yeah, so it will trace a very interesting path, and it is a very having a special name for it. What we call? Anyone?
Cyclo.
So
Cycle.
yeah,
Cycle.
cycloid. So this will first start at right angle. It goes for upward actually. It goes to the top, and maybe I need to do it from the center. So now it starts from the rest. It goes. Now this is the interesting part. It terminates at right. So the termination is always at right angle. Now it is a very common confusion that is it circular path? No. The answer is definitely it's not circle. This is look like a semicircle. No, this is not a semicircle.
Parabola.
No. So this path is called cycloid. In fact, in the examination, they may ask you only this question: that what is the path? And they may give you graph to identify which path is the correct demonstration of cycloid. So what you need to look for is that this must be right angle. The termination and the beginning must be at right angle. If it is not right angle, if I throw something like this cannot be a cycloid for this particular case. So this is called cycloid because it's come from the the cycling. You ride bicycle. So what happens? The wheel goes forward and also rotates. So that is an example of pure rolling. So when you ride a bicycle, it's a pure rolling. And because it's a pure rolling, so the path of the rim, any point on the rim will be cycloid. And this is a really big path. Now we can say this length must be bigger than 2 pi r, correct? So now we are
So
interested
that
in
length
finding,
should be pi r.
pardon,
That length should be pi r, not 2 pi r.
which length? The bottom one.
Yeah, you have written.
Bottom one,
That
the,
point is
the bottom one is 2 pi r only because it is making one complete rotation. So in one complete rotation, you unwrap by 2 pi r. Understand? So the ring will unwrap. So look at the subsequent motion. So what we are going to do is we are going to draw the subsequent motion of the ring. So after some time, it is quite possible that the point on the perimeter has come here. That's it. After some time, and now this point, if I go from center, this is the angle that it has turned back by theta. So this length must be how much? Can you guess the length? This length?
So it will be r theta.
R theta,
Exactly.
huh?
Exactly. This is r theta, and this is the center of the circle. So if I take the point and if I call this coordinate as x comma y, can you tell me what is the value of x and what is the value of y?
What is value of? Acha,
What
x
is
comma.
x? The x coordinate. How much? Anyone? No.
Okay. So what did you ask? Can you please repeat?
What is the x and y coordinate in terms of r and theta? I want the answer of x and y
R
coordinate.
theta minus r cos theta.
Yes.
Sorry, r sin theta.
Correct. Very good. So this is r
Minus,
theta
minus
minus r. Very good. So what is the y coordinate?
sir r minus
Uh, R minus
Tell me.
R cos theta.
Very good. I can take r common, this is theta minus sin theta. And if I take r common, so 1 minus cos theta. So definitely this is not a parabola because in parabola we have the
Yes, sir.
quadratic relation. So you can see that in fact you cannot replace x and y. But if you try to forcefully replace theta, which is the common variable, how it will look like? So cos theta we can write as 1 minus y by r. So theta I can write as cos inverse 1 minus y by r, right? This is what I can write from here. And now let me substitute this value in here. So this looks like x equals to r cos inverse 1 minus y by r. This is dangerous. Minus sine of cos inverse. Now this kind of equation you must not have seen in your life. The relation of y and x. But this is the equation of some graph. So this is the equation of cycloid. If you want to say it, this is the so not at all required. This was asked in some 2008 Olympiad physics in the second stage Indian National Physics exam. But of course, this is not something very big deal. But the cycloid path is actually there, and it is also having the equation. So this is called the parametric equation of cycloid. So these two equations is called parametric equation of. So now you can understand easily that how the x and y. So although these are not required, but this is how we discuss. Now, once you know the x and y coordinate, can you find the velocity of the point P? So this is the point P actually. So what is the velocity of point P? Or so we can add this must be Vx I cap and Vy.
yes, sir.
But to get a Vx, we can just differentiate. It's pretty easy. What can I? Dx by dt. By
Yes.
definition of this is a dy by dt. And differentiating is not a big deal for you. You can easily differentiate. So what will you get? Once you differentiate the x component, what you get? R theta will give you d theta by dt is the omega, correct?
Omega
And the sun will give you cos theta
cos
into
cos theta.
chain rule. Okay, so I can take omega common definitely, then it's become omega. And if you differentiate the second term, it will give you uh, omega r sin theta. That's something interesting. So we are getting omega r 1 minus cos theta I cap and omega r sin theta j. This is the velocity point. How many of you have understood this part, the second part, the differentiation?
Understood, sir.
Understood.
Yes, understood, sir.
Don't worry, I'll give you the second method, which is much easier. But anyway, let's do this from the very scratch. So once we have the VP, so once we have the VP, which is omega r multiplied by 1 minus cos theta, we can find its modulus. And the modulus is pretty easy. It's omega r 1 minus cos theta whole square. So let's expand this under root, which is 1 plus cos square theta minus 2 cos theta plus sin square theta. And in fact, we know these are kind of answers. We have seen this in the kinematics quite often. This is 2 1 minus cos theta. And what is 2 1 minus cos theta? So how we can take this out of root sign?
Sir, that half angle rule.
Yes, half
What
in the formula.
Yeah, so tell me what we can write here. You just tell me the answer. What should I write?
Two sine square
Here 2
theta by
sine
2.
square
2
theta by
theta
2.
by 2.
2 into 4 into sine square theta
Half
by 2.
4 into sine theta by 2.
So that will be 2 omega r sin theta by 2, correct?
Yes, sir.
And omega r is equal to v. So if you want, you can just write as 2 vc or. So this is the, if you know the velocity of center mass, and then if you want to find the velocity of any point at an angle theta from vertical, this is answer. So theta will change from 0 to 2 pi. So theta by 2 will change from where to where? 0 to pi.
Yes, yes.
And
Yes.
in 0 to pi, we know the answer is positive. So fine, this is a positive number. So no need to worry about this. So what we got is the speed of the point. So every point is moving with this particular speed, where theta is the variable. So why we are finding this value? So let's go back to the same. The resultant velocity of this particle p at this instant must be along this tangent, because that is the path. This is the VP direction. Understood? And because this is the VP direction, which you can also verify by joining this point to the ICR.
ICR.
This must be perpendicular. You can see it's perpendicular, isn't it? So this looks meaningful because this is perpendicular, and about this point it must be on circular path. Correct. So the VP we can see, and if we can say VP, so in time dt you will traverse this much length, right? ds. So the length of the path which you can traverse in time dt will be how much? So ds equals to, we can write vp value into dt, correct?
Yes, sir.
Because what we are trying to do is we are trying to calculate the length of cycloid. So that green line you can see, I am trying to calculate its length. How big is that? Okay. So the ds is Vp dt, and now we have ds equals to Vp is how much? 2Vc sine theta dt. Now this is something very interesting. We just need to integrate. Okay. The total distance traveled will be how much? 2Vc is common. Now I'll do some manipulation which you can understand. Dt we can write as d theta by omega, because d theta is omega dt. So next, pardon?
We see sine theta by 2.
Yeah. So now what we are getting the answer? So 2Vc by omega sine theta by 2 d theta. Now this integration is not difficult because theta will go from 0 to 2 pi. And Vc by omega is what?
R.
Correct. So can you integrate this and tell me the answer?
So 4 hours. Hello.
Yes, tell me.
4 hours.
The whole integration you're saying 4 hour or only the integration part? So no, tell me what is the integration part? Is it 2?
Yes, sir.
Are you sure? Think again, think again. It's a theta by 2, so in integration when we have a coefficient, what we do? We divide by the coefficient.
We divide by
So if the integration of sin x dx is minus cos x, then integration of sin kx dx will be minus cos kx by k. Okay, plus c, plus c. Anyway. So now the integration will be 2r.
minus plus theta by 2 by.
So this will become 8r. And what you can also realize that this 8r is definitely bigger than 2 pi r, because 2 pi is roughly 6.28 and this is 8. So sorry, this is a bigger value. So the circular path is bigger than the distance traveled by the center of mass in one rotation. So this is called the total distance traveled by periphery in one rotation, which is 8r, and this is something which you must remember. 8r.
So, but why is it bigger?
Pardon?
So, why it is bigger?
Okay. Because you can see it. If I draw a straight line, if I draw curve line, which one should be bigger? I hope you have common sense. Can you compare these two? Which one should be bigger?
Cycloid.
So, yes, understood.
So there should not be any ambiguity why this is. But anyway, I mean that was a very, derivation from the scratch how I got the velocity. But doing this way is a bit tedious, so we can do it in other way, which is very easy. Now I cannot reduce the integration part, but that will remain there. But I can do something for you, which is easy for you to understand and remember. So this cycloid is very important for the chapter called magnetism. In the chapter of magnetism, we'll also study about transverse electromagnetic field, and a charged particle in the transverse electromagnetic field exactly moves on a cycloid path. So this is something which is more important there as a numerical, and the solution in magnetism chapter takes roughly 2 pages. Now this entire effort we can reduce into one line if you know this particular answer. So if you remember this discussion, then in magnetism you can do that question, which is the most challenging problem of that chapter, in just one line. Anyway, so we'll see that how. And now nowadays there are variety of other problems of magnetism which are based on the cycloid. The cycloid is not just one question, but in fact we can create a variety of questions from this concept in magnetism. So that's why this concept is very useful for JEE advanced part. For JEE means I can tell you that the max they can ask is the path shape, or I mean a small discussion about this. I mean not something very calculative. So in Olympiad and in JEE advanced, it can be I mean calculative in nature. Okay. So now what I'm saying is that the motion we know already, so it's not a big deal. We know that for everything which is moving on a, which is making a pure rotation, the path is well known. The center will move with some value v, and it will turn by omega, and v will be equal to omega. So this is something which we know for pure rolling condition, correct? So let's say at any instant the body is here. I'm just doing for the sake of you can say you can read easily. So just take a point, any point. Just take a point at angle theta. So this point will have two velocity. One in the frame of center. In the frame of center mass, what is the velocity? You know this is tangential.
Yeah.
So in the frame of center mass, this is tangential value, but the center mass itself is going forward, and therefore now it's done. This is right angle. This is theta. This will be 90 minus
90
theta.
minus theta.
So we are done. What is VP? V minus V cos theta. Correct? Which is V 1 minus cos theta. This is Vx basically. This is Vx. So Vp x component is how much? V1 minus cos theta, which is very much obvious. And Vpy component is how much? Vp sin theta. So this is 9.06 will be V sin theta. Or you can see that the angle between V, these two vectors is 180 minus theta. So I can write Vp directly. Either you can do it by the squaring and adding. This is one way of doing, or you can just write the formula of vector relation: a square plus b square plus 2ab cos theta, which is 180 minus theta. As you can see, the angle between the vector is this much. So which turns out to be 2v square 1 minus cos theta, and this will become 2v square into 2 sin square theta by 2, because 1 minus cos theta is this much, and so the answer is this much. So you can do it like this also. Okay. And similarly, you can also, okay, we can do it later. Analyze the acceleration basically. So for any pure rolling motion with constant velocity, now it is moving with constant velocity. So there is no accession of center of mass. Center mass is not accelerating, it is just moving like this. And we have just realized that this point is moving in a frame of center mass on a circular path. So the only accession will be centripetal, omega square r, because there is no other accession of the center mass, correct? So although there is no tangential accession, there is no alpha, but still it will have some acceleration, and that is equal to omega square. So we can write in short acceleration analysis. So the accession of point P in a vector form, what we can write? Want to write in vector form? This will be omega square r, then sine theta I cap, and cos theta j cap. And the modulus is definitely omega square r. So every point on the periphery or any point which is at a distance r from the center will have only one accession, that is omega square r. So when a body is moving with uniform angular velocity omega, if omega is a constant quantity, and if the body is performing the pure rotation, pure rolling motion, so when omega is constant, then you will only have centripetal accession, and that is always pointed towards the center of the body. So body is going backward and forward, that's okay, but the accession of every point will be only directed towards the center of the body, and the value will be how much? Omega square r. So I hope this is clear to all of you. Is this clear?
Yes, sir.
Yes, sir.
So now we can go to the third concept, and that is called radius of curvature. So radius of curvature for bodies performing pure rolling motion with constant angular speed on a fixed surface. Okay. So what is the radius of curvature? Then again for this you need to go back to here, and you can see the actual path is a cycloid, which is not a circle. So this is like a curvilinear path. And if you remember the circular motion chapter, for any curvilinear path, every point will be having one unique radius. Understood?
Yes, sir.
Yes.
Those who don't remember, I mean, just you need to go back to the circular motion. Every point will have unique circle. So this point will have its own circle. This will have its own circle. I don't know what is the circle, but it's all will have same different circle. So the topmost point will have the biggest circle because it's a flattest part, as you can see. And as you come towards the bottom, it will have a smaller circle. And the circle near the surface, not near, exactly touching the surface, will be 0. So this path will have a circle whose radius will go from 0 here till maximum value here, which is actually 4r, and then again 0. So in between it will have different answer that we can see how the answers are. So this is what we're going to explore here. So let's take some random point here. So I want to know the radius of curvature of this point P. It's moving with v and turning with omega, and v equals to omega. So that's the pure relation. I want to know the ROC of this point. Now, if you remember the ROC formula, which I hope you don't do.
So it's V perpendicular by square by G. So V square by G, acceleration which is perpendicular to the velocity.
So it is v square by a perpendicular. Whatever
V
is
square
the
by
accession. So whatever is the accession of point P, normal to the velocity vector is the answer. Now that is something very interesting. So what we know that the accession of any point P on a pure rolling is always toward the center. So the direction of accession is well known to you in advance. Now the problem is what is the direction of velocity? So for that reason, we can do the ICR concept that will solve this question in one line. So if I join this point to the ICR, we know exactly what is the direction of velocity. Now this is the direction of velocity. I hope you understand this, because
Yes,
with respect
90
to
degrees.
ICR, it will be pure circular motion and it must be perpendicular to this line. So if I call this as R, then this V must be equal to omega R, correct? R is the distance from the ICR to the point P. And there is a very, valid reason for doing that. So what I'm trying to find is I need to find the component of omega square R, which is perpendicular to the V value, because this omega square, this acceleration is not perpendicular to the velocity vector, correct?
Yes, sir.
So somehow I need this angle alpha. Right now I don't know what if you give me this angle, I'm done. So let's think about this angle. So this angle is alpha. This is also alpha. Why? Because this triangle is a isosceles
Isosceles.
and this is 90 degree, correct? So what we know from the angle relation that 2 alpha plus theta plus 90 must be 180.
Yes.
So basically 2 alpha is 90 minus theta. So alpha is basically 90 minus theta by 2. Well, that's okay. So we can write something. We can write something. I mean, this is actually not required, but we can write something very interesting and nice here. So I can write alpha as omega square r cos alpha, correct?
Yes.
Like a perpendicular is how much? What is a perpendicular? Omega square r cos alpha. I hope this is clear.
Yes, sir.
So what I'm trying to say is that if this is r and if this is r and if the angle is alpha, so what you can write is 2r cos alpha must be small r from the same isosceles triangle property.
Yes, sir.
Can you see that? So what is very interesting here that the cos alpha I can also replace by this form r by 2r. Okay. And now we can directly substitute here. So V and omega, we know the relation very well. So V itself is how much? Omega small r, omega square r, and what is cos alpha? R by 2r, correct?
Sir,
Yes, tell me.
so that 2r cos alpha is equal to r.
Okay, how it is? You are asking this relation.
Yes.
So if you look at this triangle, one side, two side, third side, alpha, alpha, r, r, drop a perpendicular. How much is
Oh,
this?
okay. Sir.
So 2r cos alpha equals to r. Now it's clear.
Yes.
All right. So now something very interesting happens. This r cancels out. This omega square cancels out. This r1 also cancels out. And what we're left with is just 2r. See, so simple answer. Now what is the meaning of this? The radius of curvature of any point P is twice of the distance from the ICR. That's it. Understood? So this is a very famous relation. Once you know the distance of the point from the ICR, you just twice make it double, and that's your answer. Over and now.
Yes, sir.
And what is that answer? So now, if you want to write a complete answer, 2 times in case if r is not given, if the theta is given and point P is given. So we know r itself is how much? 2r cos alpha, which is 4r cos alpha. And what is cos alpha? So this is way to remember. Remember this, and then you can derive other formulas. So then cos alpha is how much? So we have seen cos alpha is cos 45 degree minus theta by 2. Well, that's not a big deal. And then you, if you want to expand, you can expand, and if you want to keep it, you can keep it. This is the answer. So imagine if I take the theta equals to 90 degree. What does it mean? So theta equals to 90 means the topmost point, correct? So if theta is 90, the point is here. What is the ROC of this
Yes.
point? No, that's very easy to find because this is the distance from the distance of this point is
4R.
Q from the ICR is 2r, so the answer is 4r. That's simple. So the ROC of this point is very low. What is the ROC of bottom? 0,
0.
because it is ICR only. So the distance from ICR is 0, so this is 0. So that's why I said the radius of curvature will vary from 0 to 4r. So this is the ROC of this point is 4r, and this ROC is
0.
0. So the values will vary from 0 to 4r, and that is ROC value, the radius of curvature. So you can find this answer very easily. Let's say if I ask you, what is the radius of curvature of this point? What is the ROC of this point? Now this is very easy because we know the distance,
Yeah,
root
sir.
2r.
Root 2r.
Yes.
So twice of that, 2 root 2r, correct? Just double.
Yes.
So the best way to remember is find the distance from the ICR to the point, make it double, and that will give you the radius of curvature. Okay? Not good. So now we are also done with the radius of curvature. So anything else which is left in the pure rolling condition? Toppling is also discussed. We'll discuss toppling once again in chapter of torque. We have discussed the accession, we have discussed the okay, so let me discuss the last topic, which is actually I was trying to avoid, but just I'm going to mention. So acceleration analysis on a curvilinear path. Now I will not take any curvilinear path which is complex. I'll just take the circular path. So what does it mean? Imagine if you have a fixed, maybe you can think of a circular path. So now this is a curved track, and this body is performing pure rolling on this curved track. So body is having omega, and the radius is r. And it is moving on a curved track of radius capital R. This radius is capital R. And you're moving on the circle, so the surface is replaced by the curved surface. Okay. Another question is how to analyze the acceleration of the center of this circle. Okay. So now you can see that the center of mass of this rolling body is moving on a circle of what radius? Can you guess the radius of the circle?
R plus small r.
Sir.
Correct. So the radius or the path in which the center is moving is r plus r. So we have a radius of curvature, separate thing. We have a radius of the path traversed by center mass is different thing. And then we have omega. So let's take the body is also having alpha, and it's a pure rolling condition. And I just want to analyze the accession of this point P. So let me show you how to write. So it's very easy. You first analyze the accession in the frame of center of mass.
Omega square r plus alpha r. Sir, but for pure rolling only omega square r will be there, no?
Okay, tell me. Once again. So in the frame of center, the accession we know, well known, it's a two accession. Which one?
Omega
Tangential
square r.
and centripetal. So it will have alpha r here and omega square r here. Correct? But the center of mass itself is moving on a path which is circular path. So center mass also will have two values. One centripetal and other is tangential. Tangential we know already. So what is the value of tangential? The tangential is also alpha. But the centripetal will be something interesting. It is Vc square by r plus r. So this is the V square by r. Now what is Vc by the way? So Vc itself is how much? Omega r. Because of the pure rolling condition. This is the bottom, and we can say Vc is omega r. So the acceleration of the point P will have two value. So alpha r I cap and omega square r minus j cap because of the center of mass frame. And the center mass itself will have alpha r I cap and Vc is square by r plus r minus j cap. And now you can just substitute the value. So alpha r becomes 2 alpha r I cap and this becomes omega square r minus j cap plus what is Vc square? Omega square r square by r plus r. So this is the answer. Okay.
Sir, I don't understood that VC square by R plus R.
Oh, that's nice. So again, that's why I say always study the circular motion chapter. So in a circular motion chapter, we have a centripetal accession, and what is the formula for that?
V square by R.
V square
Mm.
by R.
So this is what I did. So what is
Okay.
the circle? In which circle the center mass is moving?
R plus R.
So what is its centripetal accession?
VC square R plus R. Okay.
E square by r plus. Okay.
So
So
then
what
the
we are doing is
tangential will be alpha R.
okay. That's the problem. So in a pure rolling condition, if the center mass is having a acceleration and if the angular acceleration is alpha, then what is the relation between these two? A equals to
Alpha R. Oh yeah, sorry.
because of the similarity of the answer, so you get confused. This is the same answer here, same answer here. But what we are doing is two separate analysis. That's why I have to use the color coding. So you can realize that first I'm trying to explain the acceleration of the point P with respect to the center of the circle itself, the small circle. And what is we are doing next? Because we are discussing the answer from the center, let's discuss the accession of the center itself, which happens to be moving in a circular path. So again, it may have two values, centripetal and tangential. And we have found that it is indeed having two values, centripetal and tangential. So there are four separate terms, one in the frame of center of the circle and other in the frame of center of curvature of path traversed by center of mass. Like it's really complex. I can mention it's very complex. So do you realize this fact? What is happening here?
Yes, sir.
Okay. So this is how we can
Sir, I have one doubt, sir. So
Mhm.
why we took, sir, I understood the first we took point P alpha I cap and minus square and minus square. Sir, but why did we again write alpha I cap in the red?
Alpha or I cap in the red. Okay.
Yes.
So what is the tangential accession of center mass?
Achha.
Tell me. What
Sir,
is the
yes, alpha.
tangential accession of center mass? It is
Alpha.
alpha. That's it. So you have to think of tangential and centripetal for each case. And let's say even if it is a plane surface, the answer is alpha. No? So this is the tangential always. And the centripetal in this case is zero because the radius of curvature is infinite. So when you move on a flat surface, or like when you move forward like in a straight line is a circle of what radius? Infinite radius. Okay, because the straight line is a circle of infinite radius. So therefore, when something moves on a straight line, it will never have the centripetal acceleration, and that's why we never discussed about it in a rectilinear motion. So only when we study the circular motion we discuss, if you remember.
Yes, sir.
Yes.
Okay. So for if you have still some confusion, it's my suggestion. Go back to the circular motion chapter. Do watch the videos again, and hopefully that will clarify the doubts. See what we can realize through all this discussion that we never learn something new once we have finished the basic. So what we learn is basically in physics is the application, how to apply what we have learned so far in different contexts. So we are applying the concept of centripetal accession, tangential accession, but just only the context is different. So that's why the first five chapters or four chapters of physics are the only chapters which you have to reapply everywhere. So rest is called application. So when you study the magnetism, let me tell you, the entire magnetism is nothing but the circular motion. So I'm saying the entire magnetism is circular motion. That's it. That's over. The entire current and electricity is simply the work energy power and bit of laws of motion.
So electrostatics is
Entire
gravitation.
yes. So entire electrostatics is simply the laws of motion and the work energy power and everything. If you think of electrostatics is again a similar chapter as the rotational dynamics. So that includes everything and slightly more concept. That's why it's a vast. Again, if you go to the capacitor chapter, it's a energy conservation. So if you really understand energy, you can master the capacitor. If you don't understand energy, you can't master. That's it. The electromagnetic induction is purely work energy theory. So if you really understand the work energy, you can actually master that chapter. If you don't understand, it's really hard. So in physics, the chapters are very much limited. It's just 4 or 5 chapters. But in different contexts, we need to learn to reapply or apply in a way which we have never done before. And that is why you need to know the like, knowledge of that topic separately or individually to crack the question. When I will teach you, I will show you that any question of electromagnetic induction can solve by the Newton's laws of motion. Any question. So I can create a circuit and you can add the laws of motion. So you may have a circuit like this. And imagine I can write as a this is resistance, this is inductor. And those who don't know this, we can solve by the laws of motion. So you know what you can write? E minus IR. E minus IR minus KX. Oh, KX means equals to mass into acceleration. Now you will understand that this is mass, this is acceleration, this is spring force, this is drag force, this is force, applied force. What I'm writing is basically I'm writing F minus BV minus Kx equals to M into. Now you will learn how to relate these things with the circuit symbols like battery symbol, resistance symbol, length symbol, and eventually you will realize that okay, these are just a basic concept of laws of motion. But of course, you won't get this in books. So to learn these things, you have to be here only. So only in this lecture you can get to know that you can solve question of electromagnetic induction using Newton's laws of motion. So always stick to basic, and whenever you feel confused what to do next, just go back to the first 4 chapters, revise again. So as many revision you will go for the first 4 chapters like vectors, kinematics, laws of motion, and work energy power. You will become stronger in your physics always. So no need to go back to the big chapters. Just go back to those chapters and just realize more about it. How we need to add the work. So this is the analysis which is just I wanted to demonstrate, and this is done. No need to think much about it. This is only for the assignment which I have given to you. So there you need such thing to solve all questions. But even if you solve Visarma, that is sufficient for NEET examination, for JEE mains, only for advanced and Olympiad this concepts are required. So I think we are done with the kinematics. Anything else left? I don't think so. Anything else left? Motion is discussed. Velocity is analyzed. The radius of the Earth is discussed. Okay, so I think we are good to go with the next concept. So what is the next concept? So we are done with the movement of inertia, which is the derivation part. We are done with the kinematics part or the constraint relation. Okay, and okay, I will discuss one, two very important concept of constraint relation. Yeah. These are very famous problems of rotational dynamics. This is called falling stick. Falling stick problem. This is a smooth surface, and this is what I have discussed in the chapter of center of mass. That if a stick is falling, then how it will fall. So this is a stick, and let's say this it starts falling. After some time, it may be something like this. So if you remember, what was the path of the center mass? Do you remember the path of center mass?
It's a circle. A circle.
Pardon?
It is a circle.
The center mass will move right, left, or only down.
Down.
So will it move like this, or this, or this?
Sir, in the middle path, like
Yes, sir,
two,
two.
two.
So this is what we discussed. The center mass only moves downward. Why? For the obvious reason.
So because the mg acts on the center.
Because center of gravity acts.
Yes.
Because mg and normal are vertical forces, and there is no horizontal force. So therefore, the center mass cannot go right or left. We don't have forces acting on the right or left. So there is no question of center mass to move right or left. So when it will fall, it will make sure that the center mass is going exactly downward. So at any instant, the center mass will go downward with some velocity v, and it will have some omega for sure. And let's say this angle is theta. So can you tell me the length of the rod is L? Can you tell me the relationship between V and omega? What is the relationship between V and omega? This has to do
Sir,
with the
Vc
ICR.
equals to
I hope you remember how to find the relation. So first find the ICR, and then you're done. Na? The best way is to find the ICR.
sir Vc equals to L by 2 sine theta into omega.
I think that's correct answer. So that's really great attempt. So the answer is the VC is downward, so we know that ICR must be somewhere here, right? And the bottom is going this way. You can see the bottom is sliding left. So for the bottom, the ICR must be on this line. And now we got the intersection. This must be the ICR. And the distance is L by 2 sin theta, correct?
Yes, sir.
This is L by 2 sin theta. And therefore, we can directly add omega into L by 2
sin
sin theta must be equals to this. So this is the nice consideration which we need to know. So omega is related to VC. So once I give you VC, you can find the omega. And you can also find the moment of inertia about ICR. What is I about ICR? ICM plus m L by 2 sine theta whole square. Correct?
Yes,
Yes.
sir.
And this is ml square by 12 plus m square 4 into sine square. So these are the calculations that we need in future, not now, but just for the sake of analysis, I wanted to discuss. So now we can go to the next concept. That's called. So a brief introduction of torque was given to you in the chapter of vector, but we'll revisit those concepts once again for the sake of completeness, and then we'll start the solving of problem. So what is torque?
Which promotes rotation. Force which promotes rotation.
Good. So it promotes rotation. It may stop rotation also. So it will depromote also.
Yes.
Sir, it allows
So how it is promoting rotation? It's depromoting, degrading the rotation. You are moving and then you apply the brake on a bicycle, it stops. So what brake is doing? Is it supporting the rotation or opposing the rotation? Anyway, so you need to think something more on the line of laws of motion. So try to correlate what you learned in the line laws of motion. Hopefully you get the right answer.
Sir, but in that scale, balancing the scale, sir, it promotes rotation.
Not always.
Not always. Sir.
So tell me what is force?
A physical push or pull.
So you remember only what is convenient to your brain, not what is taught to your brain. So definitely in the chapter of laws of motion, I must have said a hell lot of things about force. And we had an entire one particular lecture dedicated only for the discussion about force. What is force? And in that discussion, I must not have said what you just said. It means you don't study, you just keep the things which your brain is very much at ease, remembering, not trying to teach your brain something better or something correct. Anyway, okay, so that's up to you. That's your brain. You need to think what is good for your brain. So the force, if you remember the discussion about force, it was a physical cause. It was something that it was changing the state of motion. So that was the essence of force. It changes the state of motion. So it may move the body which is at rest, and set into motion, or it may stop the moving body, it may slow down something, it may speed up. So whatever is the state, that should change. And what I said, that the state of a body is defined by velocity vector and basically called momentum vector. So momentum is something which defines your state, and when I change the momentum, I change your state. So in a way, you can say that to change the momentum, we need force. To change the momentum, we need force. Well, to change the momentum, we need force. So whenever there is a change of momentum, there is a force. So similarly, the torque having the same definition, that it is the physical cause. And similar to what the force does, it changes the translational state of body. So it can start the motion from rest of a body. When I say body, it means center of mass. So the center of mass will be start from rest. It may brought to rest, maybe speed up from one value to another value. It may slow down from one value to another value. So the whole idea is to change the state. So now the way we should remember the force is something, it's a physical cause which is capable of doing the change of state, in short, I can say. So similarly, when it comes to torque, it is also having the same purpose, to change the state only. So now the only difference is that the state that we quote here is not the translatory state, rather it is going to change the rotational state or a rotatory state of a body. And then you may argue that it must have some sort of definition, that how we define the rotational state of motion. So similar to momentum in a chapter of laws of motion, we will be defining here, which is the next topic, something called angular momentum. So angular momentum is a measurement of your state. So one value of angular momentum is one state, and the other value is another state. Now, although I have not taught angular momentum, but I know you all have learned in a chapter of Bohr's theory, where you learn that the angular momentum is quantized. And you say that every orbit will have its own angular momentum, which is the integral multiple of h by 4 pi. In a way, you're defining that each orbit is one state. And therefore, if you go from one orbit to another orbit, you change the state. So all these things are different states. So we have the discrete set of states in an atom. And because the n can go possibly from 1 to infinite, so we have infinite possible states, but all these states are discrete in value. And the larger states are insignificant, because as n goes to large value, you leave the atom at all. So all the state in the last value, they are like kind of merged together. So that's the beauty of the state definition in atom, where we have the discrete value, but in real life we have continuous state. So you can change by dt also, you can change by d value also. Elementary changes are also possible. In the world of atom, the elementary changes are not possible. What we change is the discrete values. So that's a different story altogether. So the world of atom is always discrete. The world of life in which we live is always continuous. So continuity is a large scale phenomena, or we can say macroscopic phenomena. And the discreteness is the small world phenomena, or you can say the microscopic world phenomena. And the life is in between, the discrete and continuity. You can keep on, swinging from one side to the side. So the purpose of torque is to understand that, okay, can we change the state of a body? So can I speed the angular velocity up? So can I make the omega bigger or omega smaller in value? Can I shift the axis of rotation? Can I change the direction? And if the answer is yes, we can do all these things, then the question is who will do that? So the answer is yeah, some agent will do that. So what we can call that agent? So the name has given is torque. So torque is the physical cause which when acted upon a body, then it will try to change the angular state of the body. And so the obvious question is how we define the angular state. So for that we have something called angular momentum, which is something like a definition of your state, your condition. So like in society we have the low income group, the middle income group, the high income group. So we have classification or you can say state of income or finance. Everywhere we have something to define state. The money defines the state, here the angular momentum defines the state. And of course here the state is very much continuous. You can make a slight change and the state will change. Now the nature try to maintain the state, whether it's a circular, so whether it's an angular state or whether it's a translational state, both are preserved by nature. So nature having this, you can say, natural behavior to maintain it. Changing of state is always externally carried out process. So this is the process which we need to carry out externally. We need to interfere in one way or the other, and the way we interfere we define either force or torque. So the essence of learning this chapter is that we need to understand what is the purpose of this something called torque, what it does exactly. And the answer is it will change the state. Okay, so that is the core example of state. So state, say the torque is an external agent. It's agent actually, and this must be external. So to change the state, it must bring or it must come as an external agent. So it is an agent which whenever comes or acts on a body, then it tends to change the angular state of the body. And in worst case, if you don't change the state, what you do is you create the deformation. So either you change the state or you change the shape, size or dimension, or you bring some deformation. The deformation part, as I said earlier also, we study in a separate chapter of physics. So the force or the torque, both are capable of creating two things. One is called the change of state and other is called the change of form. The form means the shape, size or dimension. The change of state we study in a chapter like laws of motion and rotational dynamics. And so the change of form or the change of dimension or the shape or size, we study as a separate topic or separate entity that we call elasticity. So you know that why chapters are divided in a logical way. So every chapter having some logic. Why we bring one concept, then the other concept, then the other concept, because they are interrelated. So we are trying to study one effect of force and torque, which is the motion part. And then once we are done with the motion part, we'll try to see how force and torque can also affect the dimension part, the shape or the size or the properties actually of matter. So that's why we study in a two separate contexts, and that's why we have a separate chapters in physics, which are well-defined chapters. So torque is now, I think by this time you should be able to understand, torque is the physical cause which can change the angular state. So now what is very interesting that if you know our planet, let's say the Earth, or even the other planet, let's say Mars or Saturn or Neptune, or Pluto is nowadays ostracized from the society of planet. So if we talk about all the planets and the sun, we know that they have been spinning on their own axis since time immemorial, since their inception. So why they're not changing their own omega? The question is why they're not able to change. And the answer is obvious, because to change we need external agent, and they never face any external agent. So if you realize that sun is attracting all the planets, So sun is able to apply the force on every planet, and so sun is able to change the translatory state of motion. So that is why every planet will have a variable momentum, because that is the state of, the way we define the state of planet. But for your surprise, the sun never creates torque, and therefore all gravitational force are not capable of changing the angular state of bodies. And because of this particular reason, every planet in outer space are spinning about their own axis, and that spin is not affected. So the obvious reason is there is no torque acting on them. So they are deprived of torque, and that's why they are able to maintain their angular state. They are able to preserve their angular state, and this is precisely will translate into the concept called conservation of angular momentum. Basically, you just preserve your property, and we say conservation of property. So all the planets in the solar system, all galaxy, all interstellar bodies, they never apply torque on each other. That's why their spin is always preserved. But although they apply force, they do not preserve the linear momentum. That's why they are moved from one place to other place. So these two effects we need to understand, that at the same time, the gravitational force changes the linear momentum, but it fails to change the angular momentum. So something is conserved and something is not conserved. So that's very interesting part that we'll discuss also in gravitation about conservation part. So the entire creation of a solar system was governed by the conservation principle. So when I will teach you the angular momentum, which is the next topic after this, I will give you the entire brief history of solar system, how it was created, and why we have exactly 9 or 10 planets, or maybe 8 planets so far. So why we don't have many more planets? Why don't we don't have 1,000 planets? So all things are governed by the basic laws of physics, and I'll discuss about those things in next topic. So present topic is torque. So technically, I can just say it is a physical cause which, when acted on a body, then it tends to change the angular state of body. So it is a physical cause which, when acted on a body, then it tends to change the angular state of body, or it may change the shape, size, or dimension of the body. Okay. So this is the torque. So torque is a cause. It's not something push and pull like a force. Force is also cause only. So you must learn the concept of physics in terms of cause and effect, not some class ninth definition. And you need to understand that what is the purpose of learning all this. Purpose should be very much clear. Then only you can solve numerical efficiently. Else you might be solving the numerical, but you have no sense of physics. That is called the blind method of solving problem. You only solve, but you don't know what is happening. And for that matter, don't worry if thousands of IITians who go to IIT, don't be in the confusion that they know physics. Out of thousand, hardly 1% knows physics. I'm saying hardly 1%. There is no guarantee that top 100 rank knows physics. There is no guarantee at all. Hardly they know. They are brilliant, no doubt about it. But brilliance has nothing to do with the knowledge. So it is a physical cause which when acted on a body, then it tends to change the angular state of body, or it may change the shape, size, or dimension of the body. So that's the definition of torque. Okay. So you may call it in a very layman's language that it is a twisting effect of a force, the turning effect of a force. You can say all this blah blah thing. So for your easiness, it is the turning or twisting. Okay, so the torque is something meaningless without. Okay, so fundamentally, the force is capable of creating this effect fundamentally, and therefore there must be some relationship between these two. So when I say torque, then it implies that torque of a force. When I say torque, it never implies absolute something out of nowhere. So torque is always defined torque due to or by a force. So there is nothing like absolute torque without a force. So force is implied. I mean, it is like understood. We know I'm saying torque, so I'm saying torque of a force. Okay. So mathematically, when we define torque, then it is the torque of a force. We don't say torque. So torque as a concept is what I wrote here. It's a physical cause which, when acted on a body, then it tends to change the angles of the body, or it may change the shape, size, or dimension of the body. Now the question is, what is torque of a force? Now that is something interesting. So what you learned in vector chapter was the torque of a force, the mathematical value. So torque of a constant force. Now this is what we are going to learn next. Now this is what you say the turning and twisting and rotational and all. So torque of a constant force we are going to define next. And see, the word constant is very crucial. I'm not going to define something variable. Only if this is true, then I can define. So let's see how we can define. So for that matter, we can take a rod. So let me take a rod. So let's say this is your rod. And what you do is, in this rod, you hinge it at one of its ends.
Call from India +9184.
So the end part is hinged.
So let's say we have a rod of length L and mass M. Oh, that's not required. And it is hinged about the one of the end. And now near the other end, you apply force. Which makes an angle theta. So we need to learn something called terminologies in torque. So we say this is O, we call this point as P. And we can join the O to P. and we call this line O to P as R or R vector. So there's a name of every, I mean, this meaning of everything. So O is called point of interest. It means you want to know the effect of force as a torque, like how much torque it can produce about a point O. So torque is always defined either about an axis or about a point O. So we'll learn soon about the axis definition. But right now we are learning the torque of a force. Okay, I should say about a point. Well, this is the first definition. So the point of interest, like I want to know the turning effect about this point. It means if you are sitting at that point O, then at what rate it is going to turn. I mean, that is the basic idea we are trying to understand. And the P is called point of application of force. So force is applied on the right side.
So there is hinge force also, no R at all.
But that is not applied force, right? So the hinge is acting on a body, which is for sure. What is the force applied? The agent. So you may ask the what is the torque of the force acting on the hinge? The answer is zero,
Zero.
because the hinge will not turn about hinge itself. Okay. So okay. So this is the point of application of force. Now the line which you join from the interest towards the application is called the R vector. So these all are well-defined definition. The next is the tip of the force, as you can see. And what we call this? This is called line of action of force. So you need to always create a mental picture of these quantities in your brain to actually solve the problem. So you must have the mental picture. Understood? So what we have the point of interest. What we have is the point of application of force. What we have is the line of action of force, and we have the R. So I want to understand that what is the turning ability of this force about the point O. All right. So what we can do is we can just resolve the force into two components, one along the R, and we can say F cos theta, and other
F sin theta.
So look at the F cos theta. What do you think? F cos theta is capable of turning, yes or no?
No.
No.
So definitely no. So we know that if you pull the point P along the R vector, it will never create the turning effect. In short, if the R and the F are parallel, the torque or the turning effect, which we represent by tau symbol, it must be zero. So I can say this implies this. But luckily here the force is not parallel. The F sin theta is exactly perpendicular to the R vector. So whether we are applying force at right angle or whether we have at least some component at right angle, there is a torque possible. If you are applying force only parallel to the R vector, then you will not have any component normal to the R, and therefore there is no question of turning or torque. Okay. Now from the common observation, we know that the farther you go, the more torque it will create. So that's a very common explanation that bigger the R, bigger the torque, isn't it? So how you can experience? So when you open the door, where you push the door, near the hinge or near the away from the hinge, like on the extreme side.
Extreme side.
So do you try to push the door close to the hinge or away from the hinge? So where you push? Near the hinge or away from the hinge?
Away.
Away, sir.
Away. Because that will facilitate the opening of the door because the torque will be bigger, correct?
Yes, sir.
So I think that is very common experience. I mean, I need not to explain further. If someone is having doubt, then you can ask. So now the torque, we can easily understand that torque is something which is proportional to how far it is acting. So of course, bigger the R, bigger the torque. And it is definitely proportional to how big the perpendicular force is. So basically, these two things are the thing which we need to combine together, and therefore, which I will prove later on, the torque is by natural defined as the product of these two quantities. So the numerical value of torque about a point O due to force F is defined as simply product of. So you just need to multiply the numbers. No need to worry about all things. So it's a product of how far and what is the perpendicular value. These two number will give you the torque. That's it. So from where the definition has come, I'll prove it later on. But right now you can understand that this is the definition. The torque is R into F perpendicular. No need to think about the vector and all. Just think about the value. Multiply R with which value? The perpendicular force.
Perpendicular force.
Understood?
Yes.
So this is pretty easy. Now I can write R, and what is F perpendicular? It is simply F sin theta for this case. And therefore, this you can write as R F sin theta. Now if you look carefully, the R vector is and the F vector is shown in the figure. The what is theta? So theta is the angle between R and F. Do you realize this?
Yes, sir.
And that is why the torque, okay, I'm omitting all the subscript because that is understood as of now. So I'm not writing O and F. So torque about, of course, about O with about O due to the force F, we can in vector form define as R cross F vector. So now you may be asking why cross. So in rotation, I mean, in case of rotation motion, we always have a sense of rotation. And the sense of rotation is well captured by the cross product, if you remember the cross product. So how this rod is going to turn in this particular case, clockwise or anti-clockwise? What will be
Anti-clockwise.
the sense of rotation, clockwise or anti-clockwise?
Anti-clockwise.
Anti-clockwise. So if you turn anti-clockwise and if you use the right hand thumb rule, so use the right hand thumb rule and turn your finger towards the anti-clockwise sense. Look at the thumb. How thumb is pointing? Outward or inward?
Upward. Outward.
Outward. So that's very much obvious. We know the R cross F will give you the outward normal, and that outward normal can be captured by the R cross F. You can check. So R cross F is exactly capturing the outward normal. The R is right, F is up. If you rotate from R to F, it will give you the outward normal, and that is why cross product is the right way to define the angular quantities, because it essentially captures the sense of rotation. So direction of torque is outward. It does not mean something is going to move that way. It means that is the axis about which the body will turn. That's the meaning of torque. So it is very confusing for in the beginning for most of the students that what is the meaning of direction of torque. So torque direction is, let's say if I say this is XY plane, so the direction of torque in this case is Z axis, which means the body will turn around Z axis. So it will turn in which plane? XY plane. That's the idea. So if a body is turning in the XY plane, the torque will be in the Z axis. If a body will turn in the yz plane, the torque will be in the either x or minus x. I say x axis. If a body will move in the xz plane, xz plane, the torque must be around the
A cap.
y. So the idea is the torque gives you the sense of rotation about an axis. Which axis it is turning, you get that idea. So when I get the torque along z axis, then I know my body is actually turning the xy plane. That's the meaning. If I say the torque is along I cap, then you need to realize that the body is turning in the yz plane. And if I give you the torque along the z cap, y axis, then you need to understand the body is turning in which plane.
So can you repeat?
If I give you that the torque is in the j cap, that is the y axis, then how the body must be moving? Parallel to which plane?
A ZX plane.
Exit plane.
So exactly that is what you need to realize, that
Yes.
the torque direction is not where the body is going. The torque direction is giving you the axis of rotation. That is the crucial thing we need to understand. So direction of torque gives you the axis of rotation, and that you need to identify very carefully. Why? Because the calculation of moment of inertia must be done for that axis only to analyze the dynamics. So torque will tell you about which axis body will turn. Once the torque gives you this information about which axis the body will turn, your job is to calculate the moment of inertia about that axis. Passing through center mass, you can draw the axis which is parallel to the that axis which torque signifies, and then pass through the center mass, and you calculate the moment of inertia. So this is the essence of the dynamics analysis. So when we discuss the dynamics very soon, then that is the part which we need to be careful about. So the torque will always give you the idea that about which axis you need to draw the or calculate the moment of inertia. So let me show you something more. So imagine if we have a xy plane. This is y-axis x, and then what I do is I draw a disk. So if I spin the disk here on this plane, I exactly know that the axis of rotation is this axis, correct? So this is the axis of rotation. The omega is acting this way. And if you put on a floor, the floor may have a friction, and this friction will try to oppose the motion by exerting a torque, correct? So now torque will oppose the omega or support the omega. Tell me.
Oppose.
So how the torque must be acting? So oppose means it must be
Downward.
opposite. Now this is the direction of torque. Now torque is this direction. It means it is opposite of omega, which means it will create the nt. If you look from the top, so the omega is in which sense? Anti-clockwise, correct?
Yes, sir.
Omega is anti-clockwise. The torque is clockwise. Can you see that? So it will experience a clockwise torque. So the sense of torque is clockwise and direction is like this. So we represent the direction differently. Direction only gives the axis of rotation. So the torque is downward, it means it is acting clockwise. That is why it is downward. So the direction is confusing. Like it is not the way it is moving, it is the direction which is perpendicular to the direction of movement. So omega and torque are opposite. That's a proof that it is going to decelerate and will stop eventually. When we have something supporting, it will become parallel. Same is with the alpha. If torque is acting in a supporting way, then alpha will have direction same as omega. If torque is opposing, the alpha will have direction opposite to omega. So direction of alpha is always in the direction of torque. So alpha direction is defined by torque. Torque defines the alpha direction. Okay. And because now we know the axis of rotation, we can easily know that which kind of moment of inertia I need. The answer is about this axis, which we know the answer, AMR square by 2. So moment of inertia which we need to solve the dynamics problem is AMR square by 2, because we know things are happening like this. Understood? Clear? So when you toss a coin, what happens? Am I audible to you guys?
Yes, sir.
Yes, sir.
So let's say you take a coin and you flip it, you toss the coin. So do you realize how the coin turns? How it spins actually? Can you imagine the axis of spin?
Yes.
Yes, sir.
So about which axis you have observed the coin to be spinning?
That diameter.
Yes,
The
sir.
Sir.
Diameter.
So the coin will always spin about the diameter, no matter what.
Because it has the lowest height.
Exactly, because it has the lowest moment of inertia about the diameter. So it is natural for a body to choose that omega, which is the lowest. So it will always pick up that axis naturally, which offers the least, resistance to the rotation. So when you toss a coin, it turns about the diametric axis, and the spin is always maintained because gravity is something which cannot change the spin. So we learned very soon that the gravity never affects the angular state of body. So that's the most fundamental thing in this chapter, and you can make a note of it. You can also tattoo it if you want to do this. You can tattoo that gravity never changes the angular state, and that is why the entire interstellar world, their omega is unaffected. So their spin is maintained across the universe. So that's the fundamental thing in entire physics, that gravity never affects the angular state. In fact, I can make this claim and a statement, and maybe I can put on a front page of a newspaper. Okay.
So gravity never affects.
Gravity never affect the angular state of motion of a body. Understood? So this will be the biggest claim that we'll consider throughout this chapter. But this claim is true for the entire universe. Don't worry about this chapter. You can always be sure that gravity cannot turn something. Okay. If gravity can turn, then that will be interesting, isn't it? So when you drop a pen, do you think it's turning? If you don't turn, if you
No,
just
sir.
drop it,
Sir.
but gravity is acting,
Yes,
Yes,
sir.
sir.
but is it turning?
Mm.
It means gravity cannot turn. That's the problem. No matter what shape you choose, you just pick up any shape, and you will be sure that the body will never rotate because of gravity. So the rotation always occurs due to some other force which is not very much obvious to you. You need to search for that force maybe. Okay. So let's say if you take a ruler and if you put on a table near the edge, and if you slide the ruler beyond the center mass, it will start falling. And at that instant, you can see it's turning. You can check, or you
Yes,
may take a pen. So it is not because of gravity, it is because of the
normal.
torque. Yeah, it is the normal which gave the torque during the falling process. So the normal creates the torque, and that's why it gives you some sort of omega before you leave the table, and that's why with that omega you continue moving forward. I mean downward actually. Gravity never turns anything. Gravity is something which is not going to change the angular state, and the reason is obvious because gravity acts at center of gravity. So for that matter, any force which passes through the center mass or center of gravity, I can say center of mass basically. So any force which passes through the center of mass cannot create the angular effect. That is the fundamental concept in rotational dynamics. And if you see something moving or rotating or having the tendency to rotate, you must realize that it is must be due to the torque produced around the center mass by other forces. So there must be some other force which is trying to create the torque about center mass. Any force which acts at center mass cannot turn at all. So anyway, we'll see that thing even more in detail during dynamics problem. So this is the first way of thinking about torque. Torque is very simple. It's a product of force and the distance of the point of application to the point of interest. And these two must be perpendicular. Now, this is not the only way to describe the torque. We have on one alternative way. So now the same question, but a different perspective. So we have the point of application, we have the point of interest, we have the line of action of force. And what we did in the last case that I resolved the force parallel to the r vector and perpendicular to r vector, and just we multiply the component which was creating the rotational effect. So the other way of doing the same thing is you extend the line of action both forward and backward, and then you drop a perpendicular from the point of interest to the line of action. So once you do so, this force seems to be perpendicular to this line or this rod. So this may be the imaginary rod. So if I replace this rod with this rod, hypothetically, then it will exactly create the same torque as the
R sin
actual,
theta.
actual rod will produce. And therefore, if this is R, this is theta. So what is this new rod and how big is this rod? The answer is
R
R.
sin theta.
And now you can see this force itself is normal to this new rod. Okay. So the torque about O we can just write as F into R sine theta. So earlier we were keeping the R fixed and will taking the component of F. You can do the reverse process as well. So don't play with F, keep it as such. Just look at the distance of the point of interest from the line of action of force, multiply this, and you're done. Okay. So these are the two perspectives of thinking about the force. So no matter how you proceed, you will get the same answer. And that is why when we solve the numerical, we always keep on switching from one context to other context, because I will search for the easier option, which is going to give me the answer the fastest way. So do I need to resolve the force or do I need to resolve the R? It totally depends. So when we'll solve the numerical very soon, I will demonstrate all this behavior effectively. Okay. And now the torque is because R and F and sine theta. So definitely the dimension of torque will be what? Dimension of R and dimension of force. Sine theta is dimensionless. So the dimension of torque is
ml square.
and the unit is what? Newton meter, force and distance. So unit is Newton meter as a torque. The CGS unit will be dyne centimeter, and 1 Newton is 10 power 5 dyne, and 1 meter is 10 power 2 centimeter. Okay. So Newton meter is also the unit of energy. So the torque is having same dimension as the energy. So energy unit is also distance in force into displacement. So dimension of energy is same as dimension of torque. Understood? 1 Newton meter is called 1 joule, which is equals to 10 power 7 dyne centimeter. And dyne centimeter is called erg. So in joule to erg relation, so I hope this is what you have studied in class 9th. Unity and dimension chapter, right?
Yes, sir.
Okay. So now we are done with the talk about a point. So this is the torque about a point, but we are looking for torque about an axis. But let's describe something more here, something more observation. What we can see here. So what if the force, the line of action is passing through the point of interest? What will happen? If the line of action and the point of interest will be same. So what if the force is passing like this? Then what does it mean?
Sir, then it will mean that the axis is also moving.
It means the torque is zero. That's it. If the line of action will coincide with the, so if the line of action will coincide with the point of, or it will intersect the point of interest. So if any by any means, if the line of action coincides with the point of interest or passes the point of interest or intersects the point of interest, it simply means it cannot turn the body, and that is obvious. Understood? Is this clear?
Yes, sir.
So what is required? The line of action of force must not pass through the point of interest. Then only we can have some separation between them, and then only it can turn the body. So now if the force is acting as at the hinge, will it be able to turn the body?
No, sir.
If you press the hinge of the door, will you be able to open the door? The answer is
No, sir.
definitely no. Oh, so that's a simple idea. Okay, so you just need to keep in mind. So you can make a note for torque, line of action of force must not pass through point of interest. So we are done with the torque about the point.
Sir, can you show previous?
I hope this is done.
Done, sir.
Oh. So the next is called torque due to constant force about an axis. So this is the next concept. So we have seen the point definition. Now we need to understand the axis definition. So what I'm planning is that I will discuss this in the next lecture because I have a lecture just after 10 minutes. So this next part we'll discuss later on. So now what you can do is you can, of course, I have shared the I think assignment for the kinematics part, the constraint part. You must solve all those questions as much as possible. And I want next class to be a discussion class for those questions. If you have some doubt, you can discuss. But make sure that you discuss in the tutorial for sure. Okay. And we'll proceed with the torque part. So we will start with the torque. Torque will have two parts basically: the static and dynamic. Okay, I think someone was left over.
Yes, sir, I was left. My network was disabled.
Okay, okay, just a minute. Okay, so no problem. So we'll now your name is there. You can just check. All right. So we'll discuss the next part called the torque about an axis in the next lecture. And our syllabus is all about torque about an axis. So just like if we found the equivalent called ICR, which is the some substitute reality of the IAOR, as for the sake of convenience of writing things. Similarly, the torque about a point is not the thing which we look for. The torque is always defined about an axis. So this is what we are going to learn in detail. So most of the question that we solve in this chapter is basically torque about an axis. And why this is so? Because our syllabus is confined to the plane motion. And because the plane is fixed, so the torque direction is also kind of fixed. So we'll see that.